we want to look at the question of whether or not a particular series converges. In other words, we're adding up infinitely many numbers. Is the end result going to be some finite number, or maybe does it head off towards infinity, or maybe does it head to nothing at all? It just keeps jumping around and never settles down for anything. So we've seen some series which are nice. Geometric and telescoping are nice series, but they're kind of special cases. If you're handed a random series, odds are pretty good we're not going to be able to find the exact value for what it is. And there are some very basic series that are famous and well known where we still don't know a nice formula. Of course, we know it to high precision, but we don't have a nice expression for it. So we have to learn to ask and answer the question, does this converge? And if so, why? So that's what we want to focus on today, and we'll do some very basic tests. Well, let's begin. So, what's our goal? Well, we want to know if something converges. And so we can do sort of the opposite and say, all right, what about, is there a way we can say when something diverges? And so we're going to start with a very simple observation. It says, suppose you're adding up a whole bunch of terms, infinitely many terms. Okay. And we know that our sum converges. Then it has to be the case that at the end, the term has to get small, so the a sub n has to be small. So we're adding up, and if what we're adding is going towards a certain value, then it's the little pieces at the end are having to be very small. Now, how do we see that? Well, one way to see this is to say, hey, look at what the last term is. How can I think about it? Well, if I add up everything to the last term, but I compare it to adding up everything up until the last term, so they're only different by that one last piece there, then subtraction says, hey, the nth term is really the difference of two partial sums. Now, why is this important? Well, when we talk about a sum converging, what we really mean is that the partial sums converge. So if our sum converges, then our partial sum, Sn, converges to whatever the sum is. Well, we'll call it L. Same thing, Sn minus 1 converges to L. So L minus L, 0. Good. Good. So we know the following. If our sum converges, the terms go to 0. Now we can do a switcheroo. There's a very fancy term for this. The fancy term is called contrapositive. And what does that mean? Well, what we have is this idea. If this first statement is true, then the second statement is true. So when we do a switch, what becomes, well, it says, hey, if the second statement is false, so now it's our new first statement, then the first statement also had to be false. So what it says is, hey, if the conclusion wasn't true, so that says the limit doesn't go to 0, then our assumption can't be true. So our sum diverges. All right, so this is a really simple test. Here we're calling it the nth term test. This has other names. This is sometimes also called the basic divergence test. And why the basic divergence test? Well, because it's really very simple. We're just asking, what's happening to the terms that we're adding up? And if our terms aren't going to 0, look, hopeless, hopeless. It can't possibly converge. Now, we have to be really careful. There's even a warning here. Warning. Okay. Be careful about what this says and what it doesn't say. It says the following. If the terms don't go to 0, then game over. The sum does not converge. If the terms do go to 0, more work, more work. So you could say, look, the nth term test says, if the limit is not 0, you're done. And you could say, if the limit is 0, well, then what does that mean? then more work, more work. All right, well, that's good, because otherwise it'd be too easy to know whether or not we could add things up. Now, it's not so obvious right away to say, can we think of something which for sure I see that the terms are getting small, but yet when I put them all together, the end result is going to be huge. Not obvious. So let's see an example. And it's a really important example. It's such an important name, such an important series, it gets its own name. Not a lot of series do. It's called the Harmonic series. So we're going to look at the harmonic sum, which is what happens when you add. What are you adding? Well, you're adding the reciprocals. 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5, plus 1 over 6, plus 1 over 7, plus 1 over 8. Dot, 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 dot. And you keep going. Now, we're going to argue a couple things. First off, the terms go to 0. Yeah, that one's pretty clear. 1 over n, as n goes to infinity, goes to 0. Easy. Easy. The second thing we're going to argue, this is pretty big. Now, it's not the easiest argument to make because even after you add a lot of terms, the end result is not a very big number. And if you add a lot of terms, it's a slightly not so small number, but it's not really huge. In other words, while it goes up, it doesn't go up very quickly. But here's our reasoning. We say, well, let's just show we can make it big. Well, certainly we'll start at the following. All right, 1, then a half. Now what's true about a half? Well, a half is bigger than or equal to a half. What? True story. All right, now at this point you're not very impressed. Steve, I knew a half was bigger than a half. You haven't done anything. Hold on. Look at the next thing. Notice that here we're grouping 2 terms. Which one is smaller? Well, it's the 1/4, and there are 2 of them. So this is bigger than or equal to 2 times 1/4. Well, wait a second. That's a half. Okay, so this is at least a half here. All right, let's go to the next one. There's 4 terms in the next grouping. A 5th, a 6th, a 7th, and 8th. Which one's the smallest? The 8th. The smallest one, the one on the end. How many are there? There's 4. So if I replaced each of them by the smallest one, this is bigger than or equal to 4 times an 8th, which is a half. I think you see a pattern, right? Now, the next group. Wow, a lot of them there. But look, there's 1, 2, 3, 4, 5, 6, 7, 8. Smallest one, 1/16. So this is bigger than or equal to 8. There's 8 terms, times replacing all of them by 1/16, which means it's bigger than or equal to a half. And you can imagine we keep going. For example, from 1 over 17, we can go all the way up to 1 over, can you see what the next one will be? Look at the powers here, 2, 4, 8, 16, 32. So if you go all the way up to 32, well, there's going to be 16 of them, and greater than 1 over 32 each, which again is a half. And of course, you can keep doing this forever and ever and ever. You can always group terms. Now, every time you do this, you're basically doubling how many things you have to group. But the good news is there's a lot of room left in infinity, a lot of space for us to play. In fact, you could say there's infinitely much space to play in. So our conclusion says, look, this sum is at least as big as 1, the first term, plus a half from the first block, plus a half from the second block, a half from the third block, and so forth and so on. So it's bigger than or equal to 1 plus a half, plus a half, plus a half, plus a half, plus a half. And there are going to be infinitely many halves that you add up. Well, that's going to be pretty big. It's going to go off to infinity. Our basic divergence test, right? Because if you add 1 plus a half, plus a half, plus a half, plus a half, what you're adding isn't going to 0. It's staying at a half. And therefore, the harmonic sum, 1 over n, diverges. And in some sense, we're going to see in just a little bit, this is right on the edge. It just barely fails. And so without a lot of work, it can actually succeed. It could converge. It just is so, so close to converging. Ugh, almost. Now, before we leave, I would feel bad if I didn't tell you, when I was a student, and I was a student at a university, and on Valentine's Day, there was the school newspaper. This was back in the day when they actually print stuff. And you were allowed, for a very small fee, to put in what they called a love line. I don't know, one or two little sentence blurb to, transmit to your significant other just how much you care. So for us, we had it, and I thought, I have a girlfriend at the time, and so I put in two of them. Now, one of them relates to this, and it said, what? Well, my love is like the harmonic sum. Why? Well, growing little by little, but infinite in the total. Who says mathematicians can't be romantic? And harmonic sum, growing little by little. Sorry. I should probably learn to not try to talk and write at the same time. But who says mathematicians can't be romantic? We are the most romantic. We see the truth of things. And here it says, look, just because you don't start with an infinite amount of love doesn't mean you won't end with it. And it might only grow a little bit at a time, but it can keep growing. It gets better. So go ahead, feel free, use this on your significant other and try it out. And let me know if it succeeds. Of course it'll succeed. All right. So we now have a really nice test, but it's very, very weak. Because if the terms go to 0, great, what do you do? And so we're going to talk about a series of things that you can do. And we're going to start by saying, hey, we like calculus, so let's think about calculus. There's something called the integral test, and it's going to be very integral to understanding how to do certain sums. Now, what is it? Well, it says, suppose you have a function which is nice. So it's continuous, it's positive, and it's decreasing. Lots of functions do that. Then we say, look at these two pieces, the sum and the integral. So the sum from some starting point to infinity of f of n, and the integral from starting point to infinity of f of x. They either both converge or both diverge. Now, before we get into the reasoning, I do want to just say there's a little bit of a, hey, you might say, oh, I'm working with the function, but if I plot it, it first goes up for a couple of, steps of time, maybe from 0 to 3 or something. Before it goes down, can I still use the integral test? The answer is yes. Even though it's not always a decreasing function, the thing is, you don't care what happens at the start. When we talk about convergence, it's always what's happening down there. The tail. That's the important thing. That's where you should be looking. And so if the long-term behavior says, in the long term, it does what we need it to do. It's nice, it's decreasing, we're good to go. All right, now, other side note. Summation, integration, it's not surprising that they're connected because they both are really about adding things up. The difference is when we talk about sums, there's sort of a discreteness involved. Whereas when we talk about integrals, we've had this sort of continuous summation going on. But at the end of the day, they're both about addition. So it's not so surprising that they're connected. So where is the connection coming from? Well, the connection says, hey, I can think of this sum as a Riemann sum. And what's a Riemann sum? Well, it's an approximation to an integral. And then I say, hey, it's really like an area. And so I can compare the area under the curve versus the Riemann sum. And what we'll see is, oh, nice things happen. So, what can we say? Well, one thing we can say is if we think about our sum, n equals k f of n, well, we can think of this Riemann sum as one of two possibilities. So in other words, when you do a Riemann sum, you have a width, which we'll think of as 1, because we're doing discrete steps of 1, and the height. Now the question is, in our width, which endpoint do we take? So if we think of here this f of n as being a right-hand sum, well, then we can plot. Then what we get is we have these rectangles. So here, this k says the height here, this is our f of k, and then times a 1, so that f of k is also the area. So that's f of k. Then the next one, well, that would be f of k plus 1, f of k plus 2, f of k plus 3, f of k plus 4, dot, 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 dot. Keeps going. So we say, oh, if I think about all these little rectangles as areas, because I could put them together and form a shape, it's underneath this curve y equals f of x, so the area is below. So we say, aha, the area corresponding to the sum is underneath the area of the integral. So what happens? If the integral has finite area, the sum must have finite area, because they both represent an area. Now, the other possibility is we say, oh, we can think of it as a Riemann sum, left-hand sum, where we're taking the left-hand endpoints. So from k to k plus 1, well, again, here the height is f of k. So that's my height, and then the width of 1. So I say, okay, look, that has area f of k. Well, what about this one right next to it? Well, what is it? Well, this next one right here, that's k plus 1. So the height is f of k plus 1. So that's f of k plus 1, f of k plus 2, f of k plus 3, dot, 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 so forth and so on. If you look, what you've actually done is the difference between this picture and that picture is you've just done a quick shift by 1 unit over. Now, we said, hey, we can think of this area of the rectangles, it's bounded above by the area under the curve. Now, look, the area under the curve is inside of the area formed by the rectangles. So, if the rectangles have a finite amount of area, the curve has to have a finite amount of area, and now we're done. Because what have we done? We said, hey, if one of them is finite, the other one must be finite. Finite sum, use this picture. Finite sum means that, so when I say finite sum, that means that the sum here is finite, not that we're only adding up finitely many terms. So if the sum is finite, then the area inside must be finite. So the integral must be finite. Okay, finite integral? Okay, then the area underneath the curve must be finite. Well, look, we can make the sum fit as an area underneath the curve, so that must be finite as well. So we're tying things together. So this is great. And you might say, well, wait, why is it great? Well, here's the fun thing. We don't have very many tools for sums, but we do have a fantastic tool for integrals. It's a really fundamental idea. You see, here we have the fundamental theorem of calculus, which allows us to handle things which have nice antiderivatives. And therefore, we can find various integrals that involve infinity. We can say, look, we know for sure that that's what's going to happen. Now, there's two important ideas that we need to talk about. One important idea says, hey, if I can say something that says, hey, this converges, in other words, I have a test which says I know something converges, it almost always has a built-in, not only do I know it converges, but I can tell you something about the error. In other words, how far do you have to go to guarantee you're close to the answer? And how does it work? Well, the idea is just to say, look, if I look at my infinite sum, I can say it's like I did a finite amount of it, plus there's the end. And here's the important thing, is we can go back to the picture, and if we scroll back one page, let's see if we can do that, we can say, look, we can think of our picture in one of two cases, and depending upon whether we want an upper bound or lower bound. But the point here is, hey, our infinite sum is a finite sum bounded by a finite sum plus this little extra bit here. So the moral is, one way we can think about what's happening is we can say, if I want to understand my infinite sum, so sum from n equals k to infinity of f of n, minus my sum where I don't go all the way. I stop at some point. And I say, well, how far am I off? What's the worst thing that could happen? Then the answer is, you look at this integral. And in the worst case scenario, this integral right here. You say, look, that's less than or equal to the integral from L to infinity of f of x dx. So the moral here says, look, if I can guarantee that this piece is small, and I can make it small, so make this small by choosing L, then that tells me, well, if I add up to whatever value of L that makes this small, then I know my answer to that finite sum is really close to the infinite sum. So make this small by a good choice of L. So that's one thing we have. We can say, aha, I have this infinite sum. I may not know the exact value, but I can be confident I'm within this amount of error because I can bound the integral, and life is good. So the second important idea, and this is probably the fundamental thing that's going to come out of the integral test, and almost always we very rarely apply the integral test after we state this. There's something called p-series. And p-series are what? Well, they're summations, n equals 1 to infinity, of 1 over n to the power p. So it's different than geometric. See, geometric is r to the power n, right? So n is acting as the exponent. Here, no. It's n is your base, n to the power p. And so it's very different behavior. Now the question is, when do p-series converge? Well, the good news is we did the groundwork when we talked about improper integrals. So from improper integrals, we said the following. The integral 1 to infinity of 1 over x to the p dx is equal to, well, it's infinity if p is less than or equal to 1, and it's finite, I won't work through the details, if p is greater than 1. So we say, all right, well, that's great. So the integral 1 over x to the p converges as long as p is greater than 1. Now, on the other hand, if you look at 1 over x to a power, that's going to be a continuous function, positive function, decreasing. And so, by the integral test, we say, aha, this sum will converge if and only if p is greater than 1. And so this is going to be our key. Now, on a side note, have we seen a p-series before? We have. P equals 1, right? That's 1 over n. So 1 over n, that's the harmonic series. That's the p-series. We said it diverged. But if you did the following, the sum, n equals 1 to infinity of 1 over n to the 1.000001. And remember, 1 over n diverged. What about this one? Converge. Even though it's like, really? It's only the 0.0000. There's almost, it's the same, isn't it? No, just that little bit of difference is just enough to tip the scales. In some sense, 1 over n is right on the edge when it comes to whether or not something converges versus diverging. So we're going to keep that in mind. Now, like I said, p-series are really important. So they're so important that we're going to put a box around it, because we're going to keep referring back to this over and over and over again. So you want to make sure you remember p-series converge as long as p is greater than 1. This is the main tool that the integral test gives us, because we're going to see that there are other things that we can do, and then in the end, oftentimes it boils down to understanding p-series. Now, there are certain series where you will want to do integral tests. Things such as if you have the sum of 1 over n times log of n times log n times, I'm running out of space, log n to the power 2. Okay, from n equals 1,000 to infinity. Doesn't really matter where you start, because look, it's not the start, it's the end, the tail. That determines it. This series, does it converge or diverge? Well, turns out it will converge, and it's by the integral test. And on the other hand, if we made this 2 into a 1, it would diverge. And so it's, again, one of those which is very, very close to the edge. So, all right, well, that's the start. The start of our test to see whether or not something converges or diverges. We will have more. There will be more to do. So we'll be back again. See you soon. Bye.